Hi all, this is Mr. Yeager again for physics. Today we're looking at the topic of friction. We're trying to focus on what types of friction are out there and then introduce this concept of what's called the coefficient of friction, which will be very, very important as we start doing all these free body diagrams. So here we go. Oh, that's just making marks. How about we actually start it? There we go. All right. So the thing is with friction, okay, I think for the most part, people only think about the bad things about friction, how friction makes things stop. Obviously, I mean, that's not a bad thing. I mean, that's a good thing. But with machinery, it creates the heat. It's all stuff that can cause wear and tear. But the thing is, without friction, there's some very essential things that we wouldn't be able to do, okay? You're not going to be able to walk, all right? You basically look like an old cartoon character with your feet flying back and forth if if you even stay up off the ground, all right? So you're not going to be able to move around at all without friction. So using wheeled vehicles, even sitting would be tough. All right, you might be able to sit down, but if you shift a little bit, you're going to slide pretty badly. Books, they come right out of your hands without friction. Okay, basically you're thinking of everything all of a sudden being worse than even ice, where you can't just grip even anything at all. Everything's just too slippery. Okay, so friction helps us take care of multiple things. So again, we've gone over the definition of friction. Friction is the force that occurs between two surfaces, okay? And these are surfaces that are trying to cross over each other, but again, they create a force moving the opposite, not moving, but in the direction opposite of the motion, all right? So it's always going to occur between two surfaces. You can't have one all by itself, like Newton's third law says, okay? When I walk, it's my foot, the rubber on my sole, pushing on the ground, and then the ground pushing back, and that allows me to move forward. All right. Obviously, again, you rub your hands together, you can obviously feel the friction. Okay, the friction's going to create that heat. We'll learn it. We'll obviously be able to use that some in energy later on. Okay, the idea of what's going to cause a negative work. All right. So this gets us to one of our main ideas for the day. There's different types of friction, okay? There is static friction. That's one type all by itself, all right? Then we have sliding, rolling, and fluid. We would call all of these kinetic frictions, okay? Kinetic frictions. As the name implies, static means still. The friction an object feels before it starts moving, and then kinetic when it is moving, all right? So we have both types. We're going to learn that we can actually calculate them the same way. They just have a different factor involved with them. Okay? So if we go through these types, okay? Static friction is, again, friction that occurs when an object is not moving. Now, the thing is, let's make this very, very clear. Static friction occurs where you are trying to move the object, but it's not moving. So there must be some sort of try to move, okay? You're trying to move the object, but it's not. It's staying in place, okay? We don't just say an object has static friction if it's completely still and nothing is forcing on it, okay? So this is what prevents an object from continuing to slide, okay? No, sorry, I'm not right there. This is again what's causing an object to make sure it maintains its position if there's an outside force applied to it, okay? So all of these are examples. The piano being held in place is static friction. Again, if you're trying to push it, all right, it keeps you in your seat, all right. Most seats are a little bit of an incline. Technically, if there was no friction, your bottom would slide straight off the back, all right. The thing is, static produces no heat or wear and tear because you're not moving yet, okay. The wear and tear won't happen until you start moving. There's not going to be any heat formed either because you're not moving. Went too far. So this immediately jumps us into kinetic friction. And again, there's different types of kinetic friction. The one that's most common is called sliding. All right? And you can really use this one to describe any type. We just get a little bit more specific with the other two. All right? So sliding friction is the result where now the two surfaces are moving over each other. Okay? They're pushing over each other. And again, this would be the idea like we have here of pushing a box. All right? On moving day, you just shove that box. It's moving a desk around. It's moving a chair around, sliding it across the floor. Okay? All of these would be considered sliding friction. Sliding friction would even be where you get your shirt stuck on a nail and you pull. That would be sliding friction. All right? It can obviously result in plenty of heat and wear and tear. because those surfaces are completely touching each other and rubbing over each other. That is sliding friction. After that, we have rolling friction. As the name implies, this means that we have some sort of wheels, okay, or round object, obviously, trying to make it move. Wheels or ball bearings, all right? Thing is, this would still be considered sliding friction, because if you think of a tire on a road, what's happening is there's this little section right here that currently is sliding over the surface, all right, and creating that frictional force, all right? But we call that rolling friction because basically the surface keeps on changing and changing and changing over as it goes around and around. So this obviously will produce a little less heat and wear and tear. And why is that? It usually will have less surface area touching. Usually. All right? Opposed to what we would say if we flattened out that whole wheel. The last type of friction we call fluid. And this would be your air resistance. Okay? You can see it listed right here. I'm having trouble spelling today. Resistance. All right? Air resistance, water resistance. If you think about going through swimming, okay, you have to have some sort of resistance in the water. Otherwise, you could go ahead and do freestyle and just be sliding across it, never going anywhere. Okay, so there's definitely that resistance due to something being a liquid or a gas. All right, and obviously a lot of engineers work with, like this example, the Olympic bike riders, trying to improve aerodynamics to help reduce that air resistance, that friction. Okay? Another example that you might have had is if you've ever been windburned. Okay, windburned, where if it's been a really windy day, especially if you've ever gone skiing on a cold day, it's already dry, your face dries out, the wind rubs against it, and you could get windburned, not even sunburned. All right? So this leads us to our other major topic. So what types of friction are there? Static friction and kinetic friction. But this leads us to a very, very important term, all right? And it's called the coefficient of friction. Now you see I have the word mu up there. That's because the coefficient of friction is represented by the symbol mu, okay? The Greek letter mu. So we don't call it mu, it's called the coefficient of friction, okay? You got to use all of that. And what the coefficient of friction is really trying to tell you is it's basically saying, what are the surfaces? All right? What are the two surfaces that are rubbing against each other? All right? Is it more difficult to put those two surfaces over each other? Okay, so it's like a difficulty level. How difficult is it to slide those two surfaces over each other at any time? Okay? So it's a weird idea. It's not so much, first off, this does not mean friction. A lot of people mess this up by saying mu is friction. That is not correct. It is not friction. It will help you determine the amount of friction. It is more dependent on the types of surfaces, okay? The surface is the key there, all right? And you're going to see a chart in just a bit where it's different surfaces. You can see whether they're more difficult to go over each other or less difficult, all right? The higher the coefficient, the higher the mu, the higher the frictional force will be. We'll see that in a formula in just a minute, okay? So there is a relationship, but they're not exactly the same. Please be careful with that, all right? So there are two coefficients of friction out there. We go by type. There is a coefficient of static friction and a coefficient of kinetic friction. All right? And it's because there is a difference between how difficult it is to make it start moving or to keep it moving. And so this is a question I always pose to class before we go to the next slide. What is more difficult? To make an object start moving or to keep it moving? Think of a car. That's usually the example I try to use. If you ever have to push a neutral car even on a flat surface, don't even worry about it on a hill. That's even harder. All right? But if you try to push that car, all right, how difficult is it to get it started moving and then to keep it moving? Which one's more difficult? Well, the answer would be it's more difficult to make it start moving. So this will be greater, the coefficient of static friction. It's more difficult to make an object start moving than to keep it moving. And so that's what we'll see right here. Okay? The coefficient of static friction is always going to be greater than the coefficient of kinetic friction. Sometimes in textbooks you might see this as greater than or equal to the coefficient of kinetic friction. For our purposes, let's just think of it as always greater than. All right, we don't need to get into that much detail with it. All right, and so what happens is when you push an object, you have to overcome the static friction. Okay, again, I'm not saying the mu, but the static friction created based on the coefficient of static friction. But once you start moving it, the frictional force actually goes down a little bit. I'm not going to say dramatically. It's not like 50%. It goes down a little bit, so that force that you're already pushing is actually making it a little bit easier for you to keep it moving. And so that leads us to the formula for mu. And I erased the k there because it doesn't matter. This is the formula for the coefficient of friction, whether it's static or kinetic. The coefficient of friction is always equal to the frictional force over the normal force. I'll write it down here. The coefficient of friction is always equal to the frictional force divided by the normal force. And so you can see the relationship here. As I have a higher coefficient of friction, I have a higher frictional force. But also what we want to notice is, how does the normal relate into this? And look how it's the normal, not the weight. This is the normal force. All right? But if I increase the normal force, all right, if I increase the normal force while keeping everything else the same, it should actually decrease the coefficient of friction. All right? So there's an inverse relationship between coefficient of friction and the normal force. Okay? Depending on the situation that we run into. All right? So this is very important to notice. Sometimes we rewrite it like this. We call it the fun formula, which is so amusing. Okay? FF equals mu times n, fun. All right? That's another way to look at this particular formula. So be able to recognize it either way. And so on this chart, you can see these. No reason to memorize any of these. Different coefficients of frictions depending on the types of surfaces going against each other. A lot of them have ranges because, again, it depends on how smooth the object can be too. All right. So you can see if I do glass on glass, the coefficient of friction is actually 0.921. All right. Generally, mu will usually be less than 1. Usually. There are some rare exceptions. I don't know if we're ever going to run into them in this class. Mu should be less than 1. So you can see glass on glass, if you ever push glass over glass, is actually very difficult. And that's because the frictional force is very high between two glass surfaces. Even though they might be smooth, it's actually very difficult to push them across. But if I look at ski on snow, look at that coefficient of friction, very small. That means the frictional force is very, very small, very little between the two. The last thing to notice, it's written at the top here not very well, is that the coefficient of friction has no units. It is just a number. It's a ratio, all right? And it should stay constant, all right? It should be a constant between two surfaces, all right? I'm not saying it's like g. G is 10 meters per second squared. I'm not saying coefficient of friction is a constant, okay, in all situations. It's a constant in its own particular situation. So even if you change the mass of the glass in glass, all right, maybe the weight and the normal force, that's the coefficient of friction should stay the same in that problem. All right, but that's what you can see here. That's what the higher the coefficient of friction, the greater the frictional force. The more difficult it is to slide the objects. If I want to have a reduced friction, well, obviously if I make the surface smoother, it should reduce the friction, all right, versus a rough surface. And then lubrication also can be used. You saw on the previous page, steel with oil on it. If you lubricate it, steel on steel with oil will make a very small coefficient of friction. With no oil, I think it goes somewhere up to like 0.2 to 0.4. So obviously increases quite a bit. All right. So adding that bit of lubricant can obviously help make the surfaces a little bit smoother. And that's it. So the main ideas for friction. All right. There's two types, static and kinetic. And then we have this new topic, this new quantity, the coefficient of friction, which depends on the surfaces and can be calculated with the frictional force over the normal. All right. Thank you.